Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Thermodynamic Properties from Volumetric Data. Before going into the details of how to estimate the thermodynamic properties from volumetric data, what we do, we have a kind of recapitulation of what we have seen in last couple of lectures. We have seen distribution of component I between two coexisting phases alpha and beta at equilibrium. So, under such conditions, let us say one particular component I has been distributed between two or more coexisting phases. Those phases are at equilibrium. So, then how this component I is being distributed in all coexisting phases, those calculations we are aimed to see. So, for that conditions, for that reason what we have seen that chemical potential of that particular component has to be equal in all coexisting phases at equilibrium. That is what we have seen, right. So, then according to that one, what we have seen, we have also derived this chemical potential of that particular component I has to be equal in all coexisting phases at equilibrium. That derivation also we have done, that is, let us say if we have taken only two phases, mu I alpha is equals to mu I beta. This is what we have derived, right. So, now this is actually chemical potential, and then it is a very thermodynamic abstract mathematical kind of variable which is not having any direct relation to the real life measurable properties such as temperature, pressure, composition, etc. Then what we have to do? We have to do some kind of arrangement so that we can make this chemical potential to be related to temperature, pressure and composition of that particular component in that particular phase, right. If you have more than two phases, for all those phases we have to make relation between that chemical potential of that particular component in each phase to the temperature, pressure and composition of all the components of in that particular phase. Those things we have to do. That is, we have also related mu I alpha to temperature, pressure and then x1 alpha, x2 alpha, etc. Similarly, we have also related that mu I beta to temperature, pressure, x1 beta, x2 beta, etc. Actually, we have not directly made a kind of relation, but we thought of that we have to make this kind of relation, right. So, this conclusion, when we came to this point, so we were clueless how to make a kind of connection between this chemical potential and temperature, pressure and then composition for each phase. So, then what we thought of? We thought of establishing these relations. In order to establish these relations, we introduced some auxiliary functions such as fugacity and activity, right. And these fugacity and activity are much closer to physical sense than chemical potential, as we have seen that fugacity can be related or can be referred as a kind of corrected pressure, right. If it is ideal gas, then fugacity is equals to the total pressure of the system. If it is a mixture of ideal gas, then fugacity of component I is equals to the partial pressure of that particular component in the ideal gas mixture. Those kind of relation that we have made between fugacity and then real life measurable variables such as here in this case pressure. So, those kind of things we have seen. So, that is what we define these auxiliary functions, fugacity and activity, and what we have seen, this fugacity is much closer to the physical sense than the chemical potential. Chemical potential, how to relate to the temperature, pressure, composition, we are not having any idea, but we made a kind of when we introduced some auxiliary functions like fugacity and activity coefficient, then we realized that we can make a relation between these auxiliary function to the temperature, pressure and composition. That is what we realized, right. And the concept of this fugacity and activity are coming from the ideal behavior, okay. So, this is also we have seen. Let us say if we have a two phase, alpha and beta phase, and if you take alpha phase as a vapor phase and beta phase as a liquid phase, then mu I alpha is equals to mu I beta. We can write it as phi I yip is equals to gamma I xi fi naught. This is also we have seen in the previous lecture, where here phi I is nothing but the fugacity coefficient, and then gamma I is nothing but the activity coefficient, Fi naught is nothing but the fugacity of component I at some fixed conditions such as standard states. In general, it is taken as a kind of saturation pressure Fi naught for majority of the cases, but however, it depends on the what reference state that we have taken. So, that those things we again get into the details when we discuss about the liquid mixtures. And then this transformation, whatever transformation from the chemical potential to the activity coefficient or fugacity coefficient like this as shown here in this equation, that is coming from the concept of the ideal behavior of the system. As I said, if you take a kind of pure gas, then fugacity of that particular gas is equals to the total pressure of the system, provided the gas is the ideal gas. Okay. And then if you have a kind of mixture of gases and then that mixture is obeying the ideal behavior, then fugacity of any component I is equals to the partial pressure of that particular component. That is the basis that we have taken in order to get this transformation. Okay. So, that we can have a kind of transformation from the chemical potentials to these auxiliary functions, and then also simultaneously we have a relation between these auxiliary functions and temperature, pressure and composition of the system. Okay. Now, for mixture of ideal gases, phi is equals to 1, fugacity is equals to the total pressure for the pure gas if the gas is ideal gas. If it is mixture of ideal gases, then fugacity of any component I is equals to the partial pressure, but the fugacity coefficient is equals to 1, Okay. So, that means if ideal behavior is there, so then this fugacity coefficient should be 1. Similarly, if you have ideal liquid mixtures at low pressure, then activity coefficient gamma I should also be equals to 1. That means, at the ideal conditions, both of these things are equal to 1. That is what the limitation of this fugacity and activity coefficient that we have. Okay. Fi naught is given by saturation pressure of pure liquid I at temperature of interest, and these auxiliary functions are numerical factors of the order of unity that establish the correction between the real mixtures and those by ideal mixture. So, let us say if phi I is equals to 1, then we can say that it is a kind of ideal gas mixture. If it is more than 1, then we can say that there is a kind of non-ideality is there, and then how much is non-ideality, that depends on the magnitude of this phi I that we are going to measure. Okay. So, this phi I and then gamma I are going to give a kind of information how much are they away from the ideal behavior. Okay. If they are equals to 1, then we can say that the both vapor and then liquid phases are kind of ideal behavior, they are obeying ideal behavior. If they are not equals to 1, then we can say there is a non-ideality, and depending on the magnitude of this phi I and gamma I, we can say how much non-ideality is there, how strong is the non-ideality in the given vapor or liquid phase respectively, depending on the phi I and then gamma I values. Now, in reality, for most cases we cannot assume ideal behavior obviously, and must establish following two relations, that is phi I is equals to function of temperature, pressure y1, y2, some function f of f phi, and then similarly gamma I function of temperature, pressure x1, x2, that is composition, some function f gamma. So, what are these functions? Unless if you know these functions, you cannot solve this problem. Let us say two phase, whatever that information we have, yi phi I p is equals to xi gamma I fi naught. If you wanted to solve this equation for non-ideal system, actually for non-ideal system we should know this phi I and then gamma I, then only we can solve this problem, and then only we can solve this equation and then get what is xi and yi, that is how this ith component is being distributed between these two phases at equilibrium, that you can calculate it, that you can calculate only when you know what is this phi I, what is this gamma I, right. And then we understand these are functions of temperature, pressure and then composition. So, the aim of this particular lecture and then coming two lectures is nothing but establishing some kind of relations for this fugacity coefficient. Later on we will be having information on how to establish this relation between activity coefficient and then temperature, pressure and composition, but next few lectures we will be concentrating on this particular lecture. Okay. Now, already as we are saying that phi is equals to 1 for ideal gases or ideal gas mixtures, then when we use PV is equals to RT and then calculate the fugacity coefficient, then we will get 1. So, if the mixture is not a kind of ideal mixture, but it is a real mixture having some non-ideality. So, then how to get this phi information? That is what the aim of this particular lecture, and that information we can get if we know information about the volumetric data of the system. Volumetric data in the sense some information about the PVT information like pressure, function of temperature, volume and composition, or volume function of temperature, pressure and composition. Such kind of information, if we have that information, we can use in order to get this fugacity coefficient. And there are a few relations, those relations that we are going to derive now, and then we take a kind of example cases. Let us say van der Waal, a gaseous mixture which is obeying a van der Waals equation of state, which is displaying some amount of non-ideality at moderate pressure. So, for that van der Waals equation at moderate pressure, what is the fugacity coefficient for the mixture of gases as well as the for the case of pure gas obeying this van der Waals equation. That is what we are going to do in this particular lecture. So, in order to get these functions phi as a function of temperature, pressure, composition, we need to have a kind of a volumetric data information. Okay. So, thermodynamic properties from volumetric data. Most thermodynamic properties of interest of any substance, regardless of whether it is pure or a mixture in a phase equilibrium, can be calculated from thermal and volumetric measurements. Thermal measurements in general, that is about the heat capacities, give information as how some thermodynamic properties vary with temperature, whereas the volumetric measurements give information on how thermodynamics properties change with pressure or density at constant temperature, Okay. That is, if you have an information this V as a function of temperature, pressure and composition, or if you have this function P as function of temperature, volume and composition, then we can make use of this information, either of these information, and then we can find out any thermodynamic properties. First we can make use of Maxwell relations to get this internal energy or enthalpy etc. Once you know any two properties, rest all other properties, thermodynamic properties, you can easily find out. But our interest is not finding out thermodynamic properties from volumetric information, but making use these equations to get information about the fugacity coefficient of a component I in the mixture. Okay. So, this we are going to derive relations for this phi if you know either this function or this function. Actually they are the same, but what is the difference here? Independent variables are temperature, pressure and composition. In the case here temperature, volume and composition. So, what we do, one case we take at constant temperature and composition, and another case at constant temperature and composition again. We derive relations for phi as T and P as independent variables, and in other case we obtain relation for the same phi as T and V as independent variables. These relations we are going to derive now. So, let us say if you have independent variables T and P, then using the Maxwell relations one can obtain the effect of pressure on enthalpy and entropy at constant temperature and composition using these two relations. dH is equals to Cp dt plus V minus T dou V by dou T at constant P and T dP. Since we are doing all these things at constant temperature and composition, this condition must be remembered. Whatever the fugacity relations that we are going to derive, they are valid at constant temperature, and composition. So, since the temperature is constant, then dT is 0. So, dH is equals to V minus T dou V by dou T dP. Using this relation, if you integrate this relation, you can get the information about enthalpy, and then how this enthalpy is changing by change in pressure, or the effect of pressure on this enthalpy we can find out by integrating this equation. Similarly, ds is equals to Cp by T dt minus dou V by dou T at constant P and T dP. This is another Maxwell relation. These two are Maxwell relations only, right. Since it is constant temperature, again dt is 0. So, ds is equals to minus dou V by dou T at constant P and T dP, right. So, this equation also, if you integrate this equation, you can obtain the entropy as function of pressure, or with the change in pressure how the entropy is changing, that you can find out from by integrating this equation number 2. Once you have H and S, then you can calculate other energies, like U is equals to H minus PV. Now, H is already known. So, minus PV if you do, you get the U. Then A is equals to H minus PV minus Ts, or U minus Ts, and then G is equals to H minus Ts, and then mu I is nothing but dou G by dou Ni Tp and J. So, all this once you know H and S, then you can calculate U, A, G, these energies also you can calculate. Once Gibbs energy G is known, then you can find out the chemical potential. Then you can find out the chemical potential, mu I is equals to dou G by dou Ni Tp and J, as a kind of definition that we can take for the chemical potential evaluation, right. Because we know that once we know the chemical potential, mu I minus mu I naught is nothing but RT dln Fi. This we know it, right. So, you know the G, so then you know the mu I chemical potential. So, chemical potential at required temperature and then at reference temperature and pressure, these conditions if you get, so difference you do, then that difference whatever is there, that can be related to the Figastic coefficient of that particular component in the mixture. So, that is the reason we can get the required information for Figastic and then followed by Figastic coefficient, that is nothing but Fi by Yip, this thing we can calculate. Okay. And this RT ln d ln Fi, that we can write RT ln Fi by Fi naught is equals to mu I minus mu I naught. Fi naught is Figastic of that particular component at some standard reference state. Which one are we taking as reference state, that also makes difference. So, some of the symbols that we may be using in this and then coming lectures are Hi naught is nothing but molar enthalpy of pure I as an ideal gas, but at temperature T. Si naught is molar entropy of pure I as an ideal gas at temperature T and 1 bar pressure, and then mu I naught is nothing but Hi naught minus Tsi naught. I is pure I, and then if Fi naught we are taking 1 bar as a kind of a reference with respect to the ideal gas behavior. Okay. Ni is nothing but number of moles of I, Nt is nothing but total number of moles that are present in the system, Yi is nothing but mole fraction of I, which is nothing but Ni by Nt. Okay. Total properties are represented by the capital letters, and then whatever the molar basis, whatever the extensive properties on molar basis are there, they are represented by the smaller letters like small u, small v, small h, etc. If we have a bar, then that bar to the smaller letters, that indicates partial molar properties. Okay. So, now the most important thing, how to obtain the Figastic coefficient from volumetric data information in the volume explicit form, that is whatever the volumetric information is there, that is given as a kind of this form. Volume is function of some temperature, pressure and then compression of the system. Okay. That is known as the volume explicit form, or temperature, pressure as independent variables, right. Okay. So, then under such conditions how to obtain this Figastic coefficient, that we will be seeing first. We have this Gibbs-Duhem equation. S dt minus V dp plus sigma Ni d mu I is equals to 0. Now, this one if you write for partial molar case, partial molar properties, that is partially differentiate this equation with respect to Ni by taking temperature, pressure and mu I are as independent variables, then what we will get? Obviously, we will get Si bar small si bar dt minus small Vi bar dp plus d mu I of 1 is equals to 0. That means, d mu I is equals to Vi bar dp minus Si bar dt. Right. Now, this is the relation, this coming from the Gibbs equation, Gibbs-Duhem equation. This relation is coming from Gibbs-Duhem equation. It is very much essential, important, especially in terms of obtaining the Figastic coefficient, because this relation gives the change in chemical potential of that particular component, change with respect to changes in temperature, pressure as independent variable, right. But in our case what we are taking T constant, all these derivations whatever we are doing, here temperature is constant and then composition is also constant, number of moles of the system are remaining constant. So, obviously the second term of this equation is gone. So, then we will be having dou mu I by dou p at constant T is nothing but Vi bar, or d mu I is nothing but Vi bar dp. And then we are already having a relation for d mu I as nothing but RT d ln Fi. So, that is d mu I is nothing but RT d ln Fi. By definition this is what we are having, right. Now, if you combine these two equations, what you can get? D ln Fi is equals to Vi bar by RT dp. That means, this equation is so important that if you know what is this Vi bar with respect to change in pressure, then you can know what is the change in Figasti of that particular component. So, this is what we want, but in order to solve this equation you should know what is Vi bar, and this Vi bar you can get only if you have this V, capital V as function of temperature, pressure and composition. Okay. So, let us further go into the details of this derivation. So, but Phi is nothing but Fi by Yip, and then Fi by Pi I can write Yip is nothing but partial pressure for this system. Okay. So, now what we can write? Fi is equals to Phi Yip is equals to Phi small pi. This is what we can write, but we want ln Fi. So, ln Fi or d ln Fi we want. So, d ln Fi, in place of d ln Fi we can write d ln Phi plus d ln small pi, because Fi is nothing but Phi multiplied by small pi, and then right hand side Vi bar by RT dp as it is, right. So, now this equation we can make use when we have this information, partial pressure. So, but what we try to do? We try to have a expression purely as a function of temperature, pressure and composition and nothing else. So, we try to get over of this one also. So, for that what we do? We know small pi is nothing but Yi capital P. That means we can write ln pi is equals to ln Yi plus ln P, that we can write, right. But if you take d ln pi, then we have d ln Yi plus d ln P, and all in these calculations repeatedly I am mentioning, these calculations are for the constant temperature and composition case. If the composition is constant, so then d ln Yi should be 0. That means, for constant Yi, d ln small pi is nothing but d ln capital P, right. So, now in the equation number 12, wherever where we have d ln small pi, in that place if you write d ln P and then simplify this equation, we have this equation d ln Phi plus d ln P is equals to Vi bar divided by RT dp. So, whatever d ln P is there, that I can take to the right hand side of the equation, so that I can have d ln Phi is equals to Vi bar by RT dp minus d ln P, that I can write Vi bar by RT minus 1 by P dp, right. Now we have a more explicit kind of equation. You only thing that you need to know what is the pressure, total pressure of the system, at what constant temperature are you doing, are you calculating Figastic coefficient that you wanted to know, and then Vi bar, that is partial molar volume you need to know, that you can know from the volumetric data. Okay. So, now we have a direct relation between Figastic coefficient of component I to measurable properties such as temperature, pressure and composition. Okay. So, now let us integrate this equation. So, then we have after integrating we get this equation integral d ln phi changing from 1 to some phi value, and then right hand side dp is changing from 0 to p. When p is equals to 0, then phi is equals to 1. If p is equals to 0 or p tends to 0, that means it is ideal behavior, and for ideal behavior case Figastic coefficient is 1. So, those are the lower limits of two cases. At some pressure p, what is phi, that we do not know, that is what we are calculating. So, when you substitute these limits, then you have ln phi is equals to integral 0 to p Vi bar by RT minus 1 by p dp. Right. The same equation, if I multiply both sides by RT, then I can have RT ln phi is equals to RT ln Fi by Yip, because phi is nothing but simply Fi by Yip is equals to integral Vi bar minus RT by P dP. This is the equation that we need. So, now you can see we have a kind of a explicit equation between Figastic coefficient of component I in the mixture to the temperature, pressure and then composition of the system, right. If you wanted to know the Figastic coefficient of any component I in the system, only thing that you wanted to know, you need to know is Vi bar and at what temperature and pressure you are you wanted to calculate this phi information. Okay. So, this equation is going to be very much essential, and then you are expected to remember this equation during the entire course of this advanced thermodynamics course for the entire semester. Now, this equation enables to estimate Figastic coefficient and at constant temperature and composition via volumetric data, or we can calculate the effect of pressure on the Figastic coefficient or Figastic of a given component I in the mixture, provided if you know the volumetric data in the volume explicit form, that is V is equals to some function of temperature, pressure and composition. It has to be explicitly in this form, right. You have an equation of state something like Redlich-Kwong equation, but you cannot write that Redlich-Kwong equation as explicitly in the volume explicit form. Volume explicit form in the sense, left hand side you should have only volume terms, and then right hand side all other terms other than volume terms should be there. So, Redlich-Kwong equation you cannot write in such kind of format. So, then how to do that one? For that case we will be taking Figastic coefficient estimation by taking temperature and volume as independent variables. Those things anyway we are going to do later on anyway. So, now for the time being this equation is very much essential, and then it is used to find out the Figastic coefficient of component I in the mixture, provided you know the volumetric data, the volumetric data in the form of volume explicit form like temperature, pressure and composition as function of temperature, pressure and composition. Okay. Now, if you have a pure component, then partial molar volume is nothing but molar volume. If it is a simply one single component is there as a pure state, right. Then equation 4, whatever the equation 14 that we have developed, equation 14 is nothing but this RT ln Fi by Yip is equals to integral 0 to P Vi bar minus RT by P dP, whatever the equation just we derived, equation number 14. So, this equation in place of Vi bar we have to write Vi, and then it is pure component. So, Yi is obviously equals to 1. So, that is RT ln Fi by P, and then it is pure I. So, just to differentiate Fi from the Fi of a component in the mixture, what we are writing is we are using subscript pure I like this. Okay. So, RT ln Fi by P pure I is equals to integral 0 to P Vi minus RT by P dP, okay, where Vi is nothing but the molar volume of pure I. So, this is the equation that ln Fi by P pure I is equals to 0 to P 1 by RT Vi minus RT by P dP. If you wanted to know the Figasty coefficient or Figasty of pure component I, which is non-ideal, okay. So, this equation we have to use. Remember this equation number 14, that is for a component I in a mixture is useful when it is when the mixture is a non-ideal, okay. Obviously, if it is ideal, then phi I you will get equals to 1. Similarly, if it is not a mixture but a pure component I, then if you wanted to know its Figasty, then you can use this equation number 16, provided that that particular pure gas is in a kind of a non-ideal behavior, or that is having some amount of non-ideality, okay. The same equation we can write in terms of the compressibility, because we know Vi by RT minus 1 by P, this particular thing, and then if I multiply by P and divide by P this equation, then I can have in the right hand side PVI by RT minus 1 dP by P, and then we know this PV by RT is nothing but compressibility factor Z. So, we can have ln Fi by P pure I is equals to integral 0 to P Z minus 1 by P dP. This we can make use, okay. So, both equation number 16 and this equation are same, but only thing that this equation is written in terms of compressibility, right. So, we have seen, if we know that V as function of temperature, pressure and composition, and then taking temperature and pressure as independent variable, so we can find out the Figasty coefficient. But what is this function? We have to know. If it is ideal behavior, then we know this V as V is equals to RT by P, because PV is equals to RT for the ideal behavior. If it is non-ideal behavior, then what is that relation? What are the extra terms coming into the picture because of the non-ideal behavior? All those things one should know. And then how we can know those things? We can know only based on the molecular consideration. There is no thermodynamics involved in order to get this information. We can know this information only by experiments or by the molecular consideration, okay. So, one can easily calculate Figasty of any substance in a mixture using equation 14, provided the function of F that is given in equation 15 is known, right. But this is the main difficulty. What is F? And F need not be an analytical function. In general, sometimes tabulated volumetric data are available for individual pure gases that may be differentiated and integrated numerically to yield the desired thermodynamic functions F, that is one possibility. But this is rarely the case, especially for mixtures, because these volumetric data informations are available for mostly for a kind of pure gases, not for the mixtures. And then usually one must estimate volumetric behavior from limited experimental data that is available. Generally, no valid equation of state applicable to large number of pure substances and their mixtures over a large number of conditions, including the liquid phases. So, that means we have a large number of models. So, we have to take one by one and then use that equation number 14 by writing those equations of state in volume explicit form, and then by using that volume explicit form equation of state, find out Vi bar, substitute Vi bar in equation number 14 and get the information about the Figasty coefficient of any component I, okay. But as the data is so vast, and then diversified, the data is variations are so many that it is not possible to have a kind of one single model which is suitable for large number of pure substances and their mixtures over large number of conditions. That is not possible. There are some good equations of state useful for only limited class of substances and then for limited conditions. However, these equations almost always pressure explicit form rather than the volume explicit form. as I was mentioning that Redlich-Kwong equation, this equation if you see, you can write it as a kind of a pressure explicit form. But you cannot write as a kind of a volume explicit form. So, because of this reason for Redlich-Kwong equation we cannot use equation number 14. This is one example, there may be other cases, many cases also. So, then what we have to do? We have to develop similar kind of relations for the Figasty coefficient as temperature and volume as independent variable, right. Then under such conditions, let us say you can write those equations of state in a pressure explicit form, and then whatever that equation that we get for Figasty coefficient as temperature and volume as independent variables, in that equation we can do the simplification and get this one. Anyway, this one we are going to do in the next lecture. If you have this equation of state in pressure explicit form, then what is Figasty coefficient Phi? This we are going to do in the next lecture. Figasty of a component in a mixture of ideal gases, that we already know. For ith component of a mixture, ideal gas mixture, the Figasty is nothing but its partial pressure, okay. But however, we can prove from this equation again. So, if we have a ideal gas mixture, then PV is equals to RT, P small v is equals to RT. So, this we can write P capital V by NT is equals to RT. Small v, as I mentioned already, that is molar basis, small v is the molar volume, capital V is total volume. So, this V is equals to NT RT by P, I can write like this in this form as I given in the equation number 19. Now, what we want? We want Vi bar, that is dou V by dou Ni at constant Tp Nj. So, this equation, if you do partially differentiation with respect to Ni, you can get it is nothing but RT by P. Let us say I is equals to 1, then RT by P dou N1 by dou N1, that is 1 plus dou N2 by dou N1, and all those things are 0, will be 0. So, that is the reason the Vi bar for this case is nothing but RT by P. So, in this equation number 14, this is the equation number 14. In the equation number 14, what we have? RT ln Fi by Yip is equals to integral 0 to P Vi bar minus RT by P dP we are having. So, in place of Vi bar, we can write RT by P, and that means RT by P minus RT by P is 0. So, what we get? Fi by Yip is nothing but 1, that means Fi is equals to Yip, right. So, this is the limiting condition or limiting basis that we have taken in defining this auxiliary functions, activity coefficient and Figasty coefficient, though we know we have to get back, because these are the bases that we have taken to define these auxiliary functions. That is, for a mixture of ideal gases, the Figasty of I is equals to its partial pressure. Now, we take a mixture of real gases, right, and then try to obtain what is the Figasty coefficient, but the mixture of real gases we are taking such a way that they are isothermally mixed such a way that there is no change in volume, that is capital V sigma Ni small vi. Okay. So, this is known as the kind of Avogadro's law. If there is no change in volume when the different gases are mixed isothermally, and then obeying that there is a linear relation between capital V and then small vi, then we call it as a kind of Avogadro's law, and then from there whatever the Figasty coefficients etc. we get some kind of a new expression, we called it as a kind of a Lewis Figasty rule that we are deriving now. Assume the gas mixture follows Avogadro's law at all pressure, that is real gases. If it is ideal gas, then it is valid only at low pressures, P tends to 0, and then up to the pressure of interest. Okay. Avogadro's law states that at fixed temperature and pressure, the volume of mixture is a linear function of mole numbers, that is capital V is nothing but sigma Ni Vi, small vi. Okay. That means, in this case here Vi is nothing but molar volume of pure I at same temperature and pressure, and in the same phase, whichever phase we are taking. Another way to state Amagat's law is to say that at constant temperature and pressure the components mix isothermally, that is with no change in the total volume. If there is no change in the total volume, then obviously what we can say? We can say that partial molar volume is nothing but the molar volume of that particular component, that is capital V is equals to sigma Ni Vi. So, dou V by dou Ni is nothing but Vi bar. So, from here what we do, if you do dou by dou Ni of sigma Ni Vi, then you will get Vi. That means, what we get from here, Vi bar is nothing but Vi, that is partial molar volume is nothing but the molar volume of that particular component. Okay. So, this we make use in equation number 14, right. So, equation number 14 is what? RT ln Fi by Yip is equals to integral 0 to P Vi bar minus RT by P. So, in place of Vi bar, now we can write Vi, because capital V is equals to sigma small ni small Vi. Now, compare above equation with equation 16 for pure substances. What is that we are having equation 16, that is pure substance, that is RT ln Fi by P pure I is equals to integral 0 to P Vi minus RT by P dP, that is what we just derived. So, this is what we had, equation number 16. Okay. Now, if you compare equation number 24, that is for a real gas mixture, obeying Amagat's law, and then this equation number 16, that is for pure substance. So, then what we can understand by comparing these two equations, right hand side of these two equations are same. So, then if you equate this, compare this equation and then similarly equate the left hand side of this equation, then we get Fi by Yip is equals to Fi by P pure I, that is what we get. That means, Fi is equals to Yi F pure I. This is known as the Lewis-Figasty rule. That means, if the gases, real gases are mixed isothermally and there is no change in volume by mixing, that is V is equals to, or capital V is equals to sigma Ni Vi, that Amagat's law is being applicable, then under such conditions, if you know the Figasty of pure component I, then you do not need to do additional calculation to find out its Figasty in a mixture of gases. Simply what you have to do, you have to multiply the known Figasty of pure component I with the volume fraction of that particular component in the mixture, so that to get the Figasty coefficient of that particular component I in the mixture. Okay. So, that is Fi is equals to Yi F pure I. F pure I is nothing but Figasty of pure component I, and then Fi is nothing but Figasty of a component I in a mixture of gases. Okay. Now, what we take Figasty of a component in a mixture at moderate pressure, that is the important of that equation number 14, RT ln Phi is equals to integral 0 to P Vi bar minus RT by P dP, that relation that we derived. That relation, importance of that relation is that we can make use of that equation for the cases where there is a non-ideality. Non-ideality is there beyond the low pressure conditions, that is moderate to high pressure conditions. So, we take a case of moderate pressure condition and then we take a certain equation of state and then we apply this equation number 14 to find out Figasty coefficient. Okay, that is what we are going to do now. Let us compute the Figasty of a component in a binary mixture at moderate pressures. Consider a form of van der Waals equation valid only to moderate pressures. So, van der Waals equation, what we have? We have van der Waals equation PV is equals to RT plus B minus A by RT multiplied by P plus so and so, P square P cube terms will also be there, but we are taking moderate pressure and then we are interested to consider only this part. Let us not worry about the P square P cube terms. Now, if it is a kind of ideal behavior, then PV should be RT. There should not be any additional terms. There is a non-ideality because of the moderate pressure. So, because of that non-ideality, there is a kind of additional term here, that is that additional term is nothing but B minus A by RT multiplied by P. There are more additional terms as in terms of P square P cube, but we are not taking them. So, because of this non-ideality in the system brought in terms of these additional terms, how the Figasti coefficient is going to change? Figasti coefficient has to be 1 for ideal gases or ideal gas mixtures, but it is not for non-ideal cases. Now, we brought in non-ideality in the gases system by using this van der Waals equation of state. Okay. Now, here this A and B are nothing but van der Waals constants, right, and these A and B constants, that is van der Waals constants, are available only for a pure system, only for pure gases they are available, right. Let us take nitrogen gas at moderate pressure and there exists a non-ideality. For the sake of simplicity, let us take that case, and then that non-ideality or whatever the volumetric data of that nitrogen with respect to temperature, pressure and then composition is there. With respect to the temperature, pressure, whatever volumetric data is there, that if you make a kind of equation form, then this van der Waals equation of state is valid. Then under such conditions, how to find out this Figasti coefficient, that we are do, right. So, this A and B are available purely for nitrogen, they may be purely available for oxygen like that. But if you have nitrogen and oxygen, then for the mixture these A and B constants are not available, but they are these A and B constant for the mixtures are dependent on the composition. How much N2 you have taken, how much O2 you have taken, that makes a difference in this A B values. So, that is the reason this A and B values are available for pure components, and for mixtures we have to obtain by using some mixing rules. We have some mixing rules, that those things also we will see now. So, where A and B are van der Waals constant for the mixture. Okay. So, now this equation, if you write small v is nothing but capital V by Nt, molar volume, small v is nothing but total volume by total number of moles. That you apply here, and then you write this equation in volume explicit form, because we want this equation in a volume explicit form, so that from here we can find out V I bar is equals to dou capital V by dou Ni. This you can do and then substitute in equation number 14 and get the required Figasti coefficient relations for this equation of state. Okay. Let us have subscript 1 and 2 for two components. For simplicity, we are starting with a binary mixture at moderate pressure. Okay. Then V1 bar, so we find out what is pi 1. So, we have to know what is V1 bar. V1 bar is nothing but dou capital V by dou N1 at constant temperature, pressure and N2. There are only two components, so N1, N2 are the only moles are present. Okay. This is nothing but partially differentiate this equation, capital V is equals to Nt RT by P plus Ntb minus Nta by RT, then you will get V1 bar. So, that is dou by dou N1 of Nt RT by P is nothing but RT by P plus dou by dou N1 of Ntb, that we do not know, because what is this B for mixture we do not know as of now. Then last term is 1 by RT dou by dou N1 of Nta. So, simply this is what we are getting V1 bar. Okay. So, as I mentioned, this A and B are dependent on the composition for mixtures. So, there are many mixing rules are there. For simplicity now, for the time being we are taking this constant A for the mixture, right, is a function of composition and constants of a pure species. A1 is nothing but the constant A of gas 1, and then A2 is nothing but constant A for gas 2, and then A is nothing but the constant A for the mixture of gas 1 and gas 2, right. So, these are dependent on the composition of the mixture. So, this A is equals to y1 square A1 plus 2 y1 y2 square root of A1 A2 plus y2 square A2, this is what we get, right. So, now similarly B, B of the mixture is related to the B of gas 1, that is B 1, and B of gas 2, that is B 2. How it is related? It is related to the composition, and then it is given as B of mixture is nothing but Y 1 B 1 plus Y 2 B 2. Y 1 Y 2 are nothing but the mole fraction of component 1 and 2 that are present in the mixture. Okay. So, Y 1 is equals to N 1 by N T and Y 2 is equals to N 2 by N T. So, from here that mixing rules, whatever this A we were having A 1 Y 1 square plus 2 Y 1 Y 2 square root of A 1 A 2 plus A 2 Y 2 square. In this relations we are writing Y 1 is equals to N 1 by N T and Y 2 is equals to N 2 by N T. Then we get this equation, and then that is A is equals to N 1 square A 1 plus 2 N 1 N 2 by square root of A 1 A 2 plus N 2 square A 2 divided by N T square. So, one of the N T I have taken to the left hand side because we wanted to find out dou by dou N 1 of N T A, so that to find out V 1 bar. So, and then similarly B is equals to N 1 by N T B 1 plus N 2 by N T B 2. So, one of the N T that we are taking to the left hand side N T B is equals to N 1 B 1 plus N 2 B 2. So, that we can get dou by dou N 1 of N T B, which is required to get V 1. So, when we partially differentiate this N T A and N T B with respect to N 1 and then simplify, we get this expression, right. Similarly, the B, whatever the B relation that we have, B is equals to N 1 B 1 by N T plus N 2 B 2 by N T. This we partially differentiate with respect to N 1 by keeping temperature, pressure N 2 constant, then we get B 1 plus 0 is equals to B 1. Now, these two quantities we substitute this equation number 28, that is nothing but V 1 bar is equals to R T by P plus dou by dou N 1 of N T B minus 1 by R T dou by dou N 1 of N T A. Now, these two we just evaluated by using the mixing rules. So, we substitute here, then we have this relation, right. So, now this relation what we do, we substitute in equation number 14, that is ln phi I is equals to 1 by R T integral 0 to P V 1 bar minus R T by P dP, we are doing for component 1. So, here in place of V 1 bar, whatever you are getting from this equation number 33, you substitute here, then we will have this expression when you substitute V 1 bar. So, this is all nothing but V 1 bar. Now, here this R T by P and then this minus R T by P may be cancelled out. So, under the integration only this part is remaining. Then we have ln phi 1 is equals to ln f 1 by y 1 p is equals to 1 by R T integral 0 to P B 1 minus this particular term dP, right. Now, this B 1 B 2 A 1 A 2 are independent of the pressure, they are independent of the pressure. Okay. So, then what we can do, when we integrate, we can get integral of dP is P, because all this entire thing is constant for a given temperature, for a given constant temperature in composition, right. So, then we can get B 1 P minus this particular term multiplied by P. So, that is what this term, by integrating and substituting 0 to P limits. So, this term and this term, both of them are independent of P. So, integral of dP is P and then limits 0 to P. So, P minus 0 is P. So, that P we are substituting here, right. So, now this equation further we can write it like this by taking this N T and then square of N T you can cancel out. So, that we can write like this. Why are we doing this one? Because we have this N 1 by N T terms, N 2 by N T terms. So, for those terms we can write Y 1 Y 2. So, let us write Y 1 Y 2 for those terms. So, that is 2 A 1 Y 1 plus 2 square root of A 1 A 2 and then Y 2, and then minus A we can write minus of a1 y1 square plus 2 y1 y2 square root of a1 a2 plus a2 y2 square. So, this is nothing but a by mixing rules, right. So, why are we doing? Because I wanted to do write this equation only in terms of temperature, pressure and then constant a1 a2 b1 b2 and composition y1 y2. Okay. Now, further what we do? We simplify this equation such a way that we have only y2 terms. So, that it will be easy to check whether under the limiting conditions y2 tends to 0, what is the Figas coefficient for pure component as well, that is the purpose, okay, or otherwise this part is final, okay, further simplification may not required. Okay. So, that to have a kind of limiting conditions from the point of view pure substance, we simplify this equation either in the form of a function of y2 or function of y1. Okay. Let us do as a function of y2. So, here a1, first what I am doing, a1 I am taking common from this term and this term. So, that a1 into 2 y1 minus y1 square I can write, and then from these two terms what I am doing, I am taking 2 square root of a1 a2 as common. So, that I can have a y2 minus y1 y2, and then remaining this a2 y2 square term is as it is. In the next step, here I am taking y1 common. So, that 2 minus y1 here, from these two terms y2 I am taking common. So, that I can have 1 minus y1 here and then y2 square as it is. Next step, 2 minus y1 is nothing but 1 plus y2, because y1 is nothing but 1 minus y2. In place of y1, if I substitute 1 minus y2, I can write 2 minus y1 as nothing but 1 plus y2. And then here in the second case, 1 minus y1 I can write y2. So, y2 into y2, y2 square, and this term is as it is. Next step, what I can do, this y1 I can write it as 1 minus y2. So, that 1 minus y2 into 1 plus y2 I can write 1 minus y2 square. So, that is what I have. So, here 1 minus y2 square and then remaining two terms are as it is, right. So, now further I can write this one as a a1 and then these remaining terms like this expanding, a1 minus a1 y2 square and then remaining two terms are as it is, right. So, now what I do, next step, this a1 I take out of the parenthesis. So, that I can write b1p minus a1 p by RT as one term, and then remaining terms I can take minus common. So, plus p by RT multiplied by a1 y2 square minus 2 square root of a1 a2 y2 square plus a2 y2 square. So, that this term I can write as square root of a1 minus square root of a2 whole square, and then remaining terms are as it is, that is y2 square p by RT square. Okay. So, finally, ln phi1 we are having b1 minus a1 by RT multiplied by p by RT plus square root of a1 minus square root of a2 whole square p y2 square by RT square, or phi1 is equals to f1 y1 p is equals to exponential of b1 minus a1 by RT multiplied by p by RT and exponential of square root of a1 minus square root of a2 whole square p y2 square by RT square. So, now we can see if it is a ideal gas behavior, then phi1 should be equals to 1, but now it is not ideal because of the moderate pressure, there is a non-ideality. Because of non-ideality, there are two corrections in the form of exponential terms like this, and what we can see, the first exponential term is independent of composition, is also independent of A2 B2 constants of pure gas 2. Remember, A1 B1 for constants of pure gas 1, and A2 B2 are nothing but a constant for pure gas 2, where A and B are for mixtures, and these we obtained by the mixing rule. Now, we can see first exponent, this first correction is independent of second component, its constant, its mole fraction, nothing is coming into the picture, whereas the second term is function of so both first component in terms of A1 A2 as well as Y2 as well. Okay. So, if the non-ideality of a gaseous mixture is represented by the van der Waals equation in the volume explicit form, and then if you take that volume explicit form, only first pressure term P square P cube terms are neglected, then Figas-T of component 1, if it is a binary mixture, then we can get this one as a kind of Figas-T of that particular component in the binary mixture, right. So, we can see this phi is function of A1 A2 B1 B2 P T Y1 Y2, which are experimentally measurable quantities. Temperature, pressure you can measure, composition you can measure, A1 A2 B1 B2 also you can measure. So, auxiliary function Figas-T is directly related to the temperature, pressure and then composition of the system without any difficulty, whereas chemical potential we are unable to develop such kind of relations. Now, correction for non-ideality, first exponent independent of component 2, but not the second exponent as it contains both A2 and Y2. Let us say if you have a pure component 1, that means Y2 tends to 0. If Y2 tends to 0, then the second exponent, whatever the exponent of square root of A1 minus square root of A2 whole square P Y2 square by RT is there. So, Y2 is 0, so exponential of 0, that is 1. So, the second exponent is 1. And the second term, that second correction is 1. Okay. So, that means F pure 1 is nothing but P multiplied by exponential of B1 minus A1 by RT P by RT, right. So, substitute above equation in 35, the 35 equation is nothing but whatever that equation that we have derived. So, this is the equation number 35 in the previous slide that we derived. So, here we can write F1 by Y1 is equals to P multiplied by exponential of B1 minus A1 by RT P by RT. So, P exponential of B1 minus A1 by RT P by RT is nothing but F pure 1. So, F1 by Y1 is equals to F pure 1 and then second exponent as it is. So, F1 is equals to Y1 F pure 1 exponential of square root of A1 minus square root of A2 whole square Y2 square P by RT square. And this expression we know that Fi is equals to Yi F pure I. We just derived a few slides before, it is known as the Lewis-Figas-T rule. Lewis-Figas-T rule, that is obeying Amagat's law, that is V capital V is equals to sigma Ni Vi. Then whatever the Fi is there, that is nothing but Yi multiplied by F pure I. Now, here in addition to that one, there is a kind of correction because of a non-ideality. Because of non-ideality, there is a correction. Okay. This exponent term is correction for the Lewis-Figas-T rule, that is given by equation number 25, that is Fi is equals to Yi F pure I. Okay. This is how we have to find out the Figas-T or Figas-T coefficient of any substance in a mixture or a Figas-T coefficient of a pure component by using equation of state. If equation of state is available or the volumetric data is available in the volume explicit form, then equation number 14 we can make use, and then for that equation of state or for that volumetric data, whatever volume explicit form is given, you can find out Vi bar. That Vi bar you can substitute in equation number 14 to get the Figas-T coefficient of that particular component in the mixture. Okay. So, similarly we can do some kind of analysis for kind of pressure explicit form also, those things we see in the next class. But however, before going to the pressure explicit form, we have to make use of this equation for a pure solid or liquid phase, pure condensed phase. Now, Figas-T of a pure liquid or solid, how to find out Figas-T of pure liquid or solid or a condensed phase, that is what we are going to see now. We have already seen that ln Fi by P pure I is nothing but integral 0 to P 1 by RT Vi minus RT by P dP for a pure component. If it is a component in a mixture, then Vi bar should be there. Since it is a pure component, then Vi is here. Okay. Now, this equation is general and not limited to the vapor phase only, because while deriving this equation we have not made any assumption on the phase, whether it is gas phase, liquid phase or solid phase. So, whatever this equation 14 and then 16 that we have derived for the component I in the mixture or pure component I, they are valid irrespective of the phase, whether it is a liquid phase, solid phase or vapor phase, because we have not made any assumption while deriving those relations. So, it may be used to calculate the fugacity of a pure liquid or that of a pure solid as well. So, for a pure condensed component at temperature T and pressure P, equation 16 is written as follows. Actually, the pressure 0 to P whatever is there, we are breaking in two limits, 0 to saturation pressure and then saturation pressure to some pressure P, so that 0 to saturation pressure we can have a kind of vapor phase, and then saturation pressure to some pressure of interest beyond the saturation pressure, that is valid for the condensed phase. And at the saturation pressure this vapor phase and then condensed phase are at equilibrium, right, that we know. So, making use of that information, we are writing this equation in two parts like this, that is RT ln FIC by P is equals to integral 0 to P. Now, I am breaking it to 0 to PIS and then PIS to P. 0 to PIS limit, it is in the vapor phase. So, Vi I am writing, and then from PIS to P it is in a condensed form, either liquid or solid, right. So, for the condensed form what I am writing, in place of Vi I am writing VIC, superscript C I am using for the condensed phase, and rest everything is same. Only thing that 0 to P limit I am changing between 0 to PIS and then PIS to P, because at PIS the saturation vapor is in equilibrium with the condensed phase, okay, where superscript C refers to condensed phase and superscript S refers to saturated phase. First term on the right hand side is nothing but fugacity of saturated vapor at temperature T, but the pressure Ps, that is saturation pressure. Okay. Second term on RHS, it is a correction by increasing the pressure causing compression of condensed phase to certain pressure P. By increasing the pressure from PIS or beyond PIS, you have to do the compression by increasing the pressure, you are increasing to certain pressure P. So, there should be some kind of correction, that correction is given by this second term. Okay. At saturation pressure Ps, the fugacity of saturated vapor is equal to the fugacity of the saturated liquid or solid, because the saturated phases are at equilibrium at the saturation pressure point. That means the same equation, now what I am going to do, I am integrating this one. So, this here by definition this part is nothing but RT ln FIS by PIS, right. This is the superscript S we are using to differentiate as a kind of saturation pressure condition or saturation pressure conditions. Okay. So, that is by definition the first term in the RHS is nothing but RT ln Fi by PIS, or RT ln FIS by PIS, superscript S stands for the saturated phase. And then second term I am just writing as two parts, integral VIC dP minus RT by P dP. So, integral RT by P dP I can write it as RT ln P, and then limits are from PIS to P. So, I can write this second term as a kind of RT ln P by PIS. So, that now what I can do, I can join this RT ln and this RT ln terms in the right hand side together, so that I can have RT ln FIS by PIS multiplied by PIS by P. So, this PIS is cancelled out, and then this remaining term we are keeping as it is, because what is this VIC? What is this VIC? We do not know. Unless we know it, we cannot solve this problem. Okay. So, then we have RT also, if you take to the right hand side, then ln FIC by P is equals to ln FIS by P plus integral VIC by RT dP, right. So, this one if you take off the ln either side, so then we have FIC by P is equals to FIS by P exponential of integral VIC by RT dP integral from PIS to P, right. So, then FIC is equals to FIS by PIS multiplied by PIS. What I am doing? I am simply in the right hand side multiplying and dividing by PIS. So, that FIS by PIS I can write it as phi is, that is saturation coefficient of ith component, saturation Figastic coefficient of ith component in a pure state, and then remaining exponential term is as it is. So, that this FIC in which we are interested in finding out the Figastic coefficient of a condensed phase, that is FIC is equals to PIS multiplied by phi is, Figastic coefficient of I at saturation pressure, exponential of this particular term as it is, right. Phi is nothing but Figastic coefficient of saturated vapor. Now, that equation 39 previously reflects the Figastic of pure condensed component I at temperature T and pressure P is equal to the saturation pressure PIS at temperature T to a first approximation, but there is a correction. Indeed, there are two corrections because the pressure is going beyond the PIS. So, the first correction is that Figastic coefficient PIS that gives a kind of information or the correction for the deviation of the saturated vapor from ideal behavior, right. Below the PIS, the system is in a vapor phase, and if that vapor phase is having some non-ideality, what is that non-ideality? That information one can get by this PIS information, right. And then second one is exponential correction, also known as the Poynting correction, takes into the account that the liquid or solid or the condensed phase at pressure P different from PIS, because these two phases, the condensed phase and then vapor phase, are at equilibrium only at the saturation pressure, right. But the pressure is beyond the saturation pressure, so there must be some correction, and that correction is nothing but the exponential correction that is there in equation number 39, which is also known as the Poynting correction. That is integral VIC by RT dP whatever is there, that is our exponential of integral VIC by RT dP whatever is there, that is known as the Poynting correction. But what is VIC? It is obviously function of pressure in general, but if the range of pressure is far away from the critical conditions, then we can say that the VIC is incompressible or the condensed phase is incompressible. So, that we can say VIC is independent of the pressure, and then we can write this exponential as simply exponential of VIC delta P by RT, and delta P is nothing but P minus PIS, like this. Okay. So, this is known as Poynting correction. Okay. This is true only if the operating temperature and pressure are remote from the critical conditions. If they are operating temperature and pressure conditions are away from the critical conditions, then we can say that the VIC is independent of the pressure, or the condensed phase is a kind of incompressible phase. So, that we can say VIC is independent of pressure. So, then we can straightforward integrate that equation, then we can have this Poynting correction in this form. But how much is it important? That again one has to find out. How much is it important? That depends on the delta P, that is P minus PIS. Depending on this magnitude, we can say how much is important. If it is very small, and then expansion of some small quantities is usually 1 or close to 1. If it is very large, then it may be contributing something. So, how much small is small, that we have to make sure. Both corrections are often but not always small, and sometimes they are negligible as well. If the vapor phase is not very non-ideal or slightly non-ideal, so then phi may be close to 1, so it may be small, so then you can neglect. And then if delta P is very small, it is not very large, then also exponential correction factor, that is Poynting correction, is also small. So, in such case also that can second correction may also be negligible, right. If temperature T is such a way that the saturation pressure PIS is low, say less than 1 bar, then Phi-S is very close to unity, because if the saturation pressure is close to 1 bar or less than 1 bar, so then obviously it is possible that vapor phase obeying the ideal behavior, and then since ideal behavior is obeyed, obviously Phi-S is going to be 1 or close to 1. Okay. Now, we see significance of Poynting correction by taking some pure condensed and incompressible substance of molar volume 100 centimeter cube per mole at 300 Kelvin temperature in order to check how much important is Poynting correction. Okay. Now, if the pressure in excess of saturation pressure, that is pressure in excess of saturation pressure in the sense P minus Pis, whatever the delta P is there, that delta P is 1, then Poynting correction, that is exponential of VIC P minus Pis by RT. This if you calculate by taking VIC is equals to 100 cc per mole, then you will get 1.0040 pi if delta P is 1. If delta P is 10, then also it is 1.0405, only approximately 4%. So, that means we can say still small. So, if Poynting correction is 1 or close to 1, we can say that it is negligible. It is negligible. But now you can see when delta P increases to the 100, we can see it is 1.5, Poynting correction is 1.5, and delta P increases to 1000, then you can say it is 57. So, we can say if the delta P is small, less than 10 bar or something like that, then we can say that Poynting correction is very small, and then if you say the pressure or delta P is less than 1 bar, so then we can say it is almost negligible. That means at low pressures the Poynting correction is small and thus can be negligible, but it becomes larger at high pressures and or at low temperatures. So, in the next class we will be discussing a few problems based on the things that we have discussed in this particular lecture. The references for this lecture are Engineering and Chemical Thermodynamics by Koretsky, then Molecular Thermodynamics of Fluid Phase Equilibria by Proznich et al., then Chemical, Biochemical and Engineering Thermodynamics by Sandler, and Introduction to Chemical Engineering Thermodynamics by Smith et al. Thank you.